So the first concept we're going to go through is the concept of a walk. So in order to describe this, I'm first just going to give you an example. So let's just draw a graph here. And I'm just going to draw a complete graph because it's nice to use. It's a very small one. We have E1, E2, and E3. And we're going to use a label graph to explain what a walk is, because you are going to direct a person, almost like you start at point A, what road do you take to get to point B, where A and B are vertices and your roads are your edges. And you're going to basically tell the person step-by-step directions of where they're going to go. Exactly like you would if you were telling someone to walk somewhere. So in regards to this, say for example, you start at V1. So you say, okay, start at V1, take E1. So take E1, and you get to V2. So now you're chilling there at V2. So this, at the moment, this is a walk already. It's a description, a sequence of events that you take to get from V1 to V2. But you can go further than that. You could also have a case of start at V1, take E1, go to V2, and I just want to use a different color because I use purple elsewhere. So start at V1, take E2, E1, go to V2. Start at V1, take E1, go to V2, take E2, and go to V3. So here you are, you're describing a walk from V1 to V3. But you could also be mean and make a person just continue to go up and down the exact same road. That is technically a walk as well. So you could say start at V1, take E1, and go to V2. So start at V1, take E1, go to V2. Now go back, take E1 again, and get to V1. Now, just for funsies, let's just go take E3. So now we're taking E3, and we're going to V3. Okay, so that is also a walk. So you can double back on walks. You can also hit all the vertices on your walk. So you can keep on repeating your vertices. We did repeat our vertices there. If you have a look, V1 features there and V1 features there. We also repeat our edges. We have E1 there and E1 there. So walk is basically just an alternating sequence of vertices and edges where you start at the first vertice and you end at the other vertice. Okay, so let's write that down. A walk. We're going to let G be a labeled graph, and that is just going to allow us to describe our sequence of events. And a walk in a graph is an alternating sequence. And why is it alternating sequence? Because you start at a vertex, you say which edge you're going on, you go to the next vertex in sequence. V1, E1, V2, E2, etc., all the way to En, Vn plus 1, where your Vi is essentially your placeholder for any of the vertices in your vertices set, and your Ei is also an element of your edge set. With your Ei in this case, the way that you label your graph is going to be so that it goes from vertex I to vertex I plus 1. So this is just giving you a way that the way that they named their edges. So technically my example fits that, where we have V1 and V2 and we have E1, and E1 is going from 1 to 2. So I was that 1, then it goes from V1 to V2. So that's how they labeled the graph. So it's just an alternating sequence describing where you're going. Now, if you have a simple graph, you don't necessarily have to indicate which edges you're going on. And why is that? Because in a simple graph, remember, you don't have multiple edges and you don't have loops. So there is only, for example, the example we did is a simple graph. So for simple graphs, it would have been completely sufficient because there would have been no confusion by the user or the reader if you had just simply said V1, V2, because there was only one way to get from V1 and V2 in a simple graph. In a a normal graph that has multiple edges, there could be more than one edge that you could walk. In other words, you can get to your friend's house probably by more than one sequence of events, or one set of roads kind of situation, because there are multiple edges between you. Because roads, generally, if there was only one way to get somewhere, a lot of issues will occur. So again, when you do a walk, it is a vertice, edge, vertice, but if you describing any walks in simple graphs, you can just shove down your vertice sequences because there's only one edge between them. So one of the very important things that we're going to have to describe is how long a walk is. So what is the length of a walk? And the length of the walk is the number of edges that you transverse as you are going through your walk. Which you can relate, like it's almost like talking about distance. So if you were looking at it in that regard, it's how long you would have to walk for. So the length of the walk is the number of edges in the walk. Okay, so if you had to remember how we described this walk as a sequence, and we had the case of we had V1, E1, V2, E2, V3, and we moved on and we eventually got En and Vn plus 1. So when we're looking at that and we have this situation, you'll see you have your edges, and there are N plus 1 of them, and you'll have N edges. So you'll have sorry, I think I may have said edge instead of vertices. So the red are your vertices, you'll have N plus 1 vertices, but you'll actually have N edges, just based on that description of your walk, your definition of a walk, and the way that you labeled your graph. So the whole idea behind it is, if you can determine the number of vertices, you just have number of vertices minus 1, and that would be your number of edges, which is your length of your walk. So it's the number of edges in your walk. So let's do an example of that. So we have 1, 2, 3, 4, V1, V2, V3, and V4, and we are going to create a walk here. First, just drawing you a graph. So we have a walk described by, and this is a simple graph. It doesn't have any multiple edges, it doesn't have any loops, so when you write your walk, you just have to put in the vertices. So let's have a walk described by, so we're going to call it W1, and it's just a sequence of events. So we have V1, V2, V4. So you go from V1 to V2, V2 to V4, and again, because it's a simple graph, there was only one edge directing you there, which is why we didn't have to put the edges in there. But we have 3 vertices, which means we're going to have 2 edges. So the length of the walk, so the length of W1 is going to be equal to 2. So let's do another walk. Let's do W2. And let's say we go V1, V2, V1, V4, V3. Okay, so we go V1 to V2. We go from V2 back to V1. Then we go from V1 to V4 and V4 to V3. So how many edges did we transverse? Well, we have here 1, 2, 3, 4, 5 vertices in this walk. Well, we hit 5 vertices as we go through the walk. So we're going to actually have 4 edges in this walk, right? So the length of walk 2 is equal to 4. So we transversed 4 edges. And when you look at the drawing, at first you're going to be like, well, I only see 3, but you have to remember you go from V1 to V2, then you go back, so that's another edge. And I went and rubbed everything out. So again, you go from V1 to V2, so that's one edge, then you come back to second edge, then you go to V4, third edge, and then V3, fourth edge. Okay, so you can count the number of vertices in your vertices sequence for the definition of your walk and subtract 1, and that will be your length. Right, so one of the next important things to note is the difference between an open and a closed walk. So an open walk is basically where you don't end up at the same location as where you began, and a closed walk is basically when you essentially closing the loop or the walk that you're going on, and that's actually the reason I spoke like that now, is it shows you why some people refer to a loop as a self-loop. I converted into more of a computer science way of describing the definitions. Okay, so let's go through this. We have an open and a closed walk. An open walk, basically you just don't end up in the same place that you began, and a closed walk, you end up in the same place that you began. So a walk is said to be open if its initial and terminal vertex, in other words, the vertex it ends at, are different. And then we have our closed walk and our closed walk. So if our initial and terminal vertex is the same, initial and terminal vertex is the same, it is a closed walk. Okay. So remember I spoke about the fact we're going to narrow down the definitions of walk to more, have more boundaries in the definition. So we have a walk, and now we are going to introduce the concept of a trail. Now, a trail is a situation where basically you don't double back. So by that we mean you don't double back on the same road that you took. So in other words, you don't repeat edges. So no repeated edges. Okay, so you have a walk, and a walk allows you to basically just go up and down the same road over and over, and that's you going for a walk. A trail is where you don't go up and down the same road. So no repeated edges, in other words. So the official definition is a walk, and not wall, walk, with no edges repeated. So that is a trail. So let's do an example or two. So we have V1, V2, V3, V4. Let's just side note, what kind of graph is that? Okay, so we have V1, V2, V3, V4. Let's do a walk. W1, and we're going to call W1 from V1 to V2, back to V1 to V3. Then we're going to have W2, which is V1, V2, V3, and W3, which is V1, V2, V4, V3, V2. Right, so let's go through and figure out which one of these are walks and which one of these are walks, but they also can be narrowed down to a type of walk with no edges repeated, called a trail. So the first one we have V1, V2, V1 again, and then V3. So we're going V1 to V2, we're going back along that edge to V1, and then we go to V3. So that one has an edge that is repeated. So this is a walk, but it's not a trail. Okay. And I'm going to try and very carefully rub out the red here. Right, so let's do the next one. So the next one is W2, which goes V1, V2 to V3. So V1 to V2 to V3. So that is a walk. And is it a trail? So do any edges repeat? So you go from V1 to V2, V2 to V3. There are no repeated edges, and it is a trail. Okay, so next up is the blue example. So again, I'm just being very careful here, rubbing that out. So let's go ahead and go through this. So we go from V1 to V2, V2 to V4, V4 to V3. And when you're doing the walk, you can also put arrows to show which way you're going. V3 to V2. So if you look there, all your edges only have one direction going through them. So you're going from V1 to V2, V2 to V3, V2 to V4, V4 to V3, and V3 to V2. So you're not repeating any edges. So firstly, you know it's a walk, but you're not repeating any edges, and it is a trail. Now, one thing you'll be like, the vertices are repeated. Sorry, I highlighted the wrong vertice. You have V2 that's being repeated. That is allowed in a trail. The only thing not allowed is no repeated edges. And this is going to give us, or bring us to our next definition. So the next definition we're going to look at is actually a path. And a path, so now we have the walk. Let's just write that down. We have our walk, and then we have our trail. And a path is going to narrow down even further. Well, it's going to narrow down a bit. And the idea of a path is that you generally don't go or cut through. So you don't go back or cut through anywhere you've already been. So you wouldn't like go to the post office, travel around making sure you don't take any edge, and then go to the post office again and then continue on. So you don't visit the same place. So previously you wouldn't visit the same road. Now with a path, you don't visit the same place. And which that means in graph theory terms is no vertices are repeated. So once you visited a vertice, you don't ever go back to that vertice, except possibly the initial and terminal vertex. So you can have a closed situation where your beginning point and your end point are the same, but no other place on your path is allowed to repeat. So except possibly the initial and terminal vertex. And that is to allow for the definitions of open and closed. We will go through what a closed trail is called in a bit, and what a closed path is called in a bit, once we've handled the definitions of a trail and a path, and what is the differences between them. So let's do an example. So V1, V2, V3, and V4. Let's do the graph we're really starting to appreciate. Okay, let's draw some examples. So we have walk 1. It's V1, it's V2, it's V1, and V3. I'm not going to do the exact same examples as before, but I'm going to do similar ones. Walk 2, we have V1, we have V2, we have V3, we have V4. Then we have V2. And walk 3, we have V1, V2, V3, and V4. And that's a 1, just by the way. So let's go through those and figure out what they are. So first one, we have V1 to V2, back to V1, and to V3. So we go that route, and then we go that route, and then we go that route. So that's a walk. Is it a trail? No, you repeat that edge V1, V2, so it's not a trail. And is it a path according to this definition? No, because it repeats the vertices. So once you see that, and it's not happening at the beginning and end only, then it is not a path. So this isn't a path. Okay, so let's do the next one. Let's just see if I can. Okay, that didn't go as well as I hoped, but we can always draw that line back in. So let's go through. Walk 2. You go from V1 to V2. Then you go to V3. Then you go to V4. And then you go to V2. Right, so you know it's a walk. Is it a trail? Now, you can immediately look here, you can be like, there are only arrows going in one way. So that is a trail, there's no repeated edges. Is a trail? Is it a path? So, a path, no vertices are repeated except possibly the initial and terminal vertex. So here you have V2 being repeated. So it's not a path. Okay, so let's just clear up our image again so we can do the next example. Let me just redraw it. Be a lot quicker. Okay, so next example. We go from V1 to V2, V2 to V3, and V3 to V4. So what's happening here is no edges are repeated and no vertices are being repeated. So you have it to walk, it is a trail, and it is a path. So well, let's do one more example, and that example is just the case of, let's actually have a path where the initial and terminal vertex repeat, so you can just see that what that is. So if we had to do that, we just bump up this one a bit, and we say V1, V2, V3, V4, and then back to V1. So the moment it's back there, it is a closed path. So the only time it's allowed to repeat vertices is if the beginning and end vertex is the same. So that's a closed path. And this brings us to the definition of a closed trail and a closed path. Okay, so our last definitions that we're going to look at are the definitions for closed paths and closed trails. So we know what a closed walk is, but now we're going to give you more names to describe the things such as a closed trail and a closed path. So, a closed trail is a trail where your initial and terminal vertex are the same. And terminal vertex are the same. Those are the main things that define it. But we have a special word for a closed trail, and that is a circuit. So refer to it as a circuit. Okay, so a circuit is a closed trail. What does that mean? It is a walk in which there are no repeating edges where the initial and the terminal vertex of the walk are the same. Okay, so a circuit is just a closed trail, and you know what the definition of a trail is, so you know the whole definition of a circuit. But there is a way where you can, where you talk about a simple circuit. Now, a simple circuit takes it one step further. And the whole idea with a trail, you have no repeated edges. So a simple circuit is a situation where you have no repeated edges and no repeated vertices. In other words, it is a closed path. Closed path. Okay, so it is, when you talk about a closed path, you will have no repeated vertices. Because you don't have any repeated vertices, and if you're working in the landscape of a simple graph, you would then not be able, you would then automatically fit into the definition of a circuit. So that's where this whole, it's a circuit and it's a simple circuit comes around in, because the people are working in the domain of simple graphs. And in the domain of a simple graph, you will then have a situation where if you have no vertices repeated, you'll have no edges repeated. So it will automatically have a case of your walk, your trail, and your path. And yes, everything just suddenly disappeared there. Your walk, your trail, and your path. Your path can be a trail, and it can be a walk. But your trail can't be a path, so it can't go backwards. But that's only in the concept of simple graphs. Another word for a closed path is a cycle. So more commonly, you would see a closed path being described as, and again, the words are getting a bit weird there. You'll see a closed path being described as a cycle. So overall, what you need to know, a circuit is a closed trail and a cycle is a closed path. And that's it. And that's actually where I think we stop for this week.